All right, so let's go over question 6 from section 1.1. So we're given a function that gives us the height of a bungee jumper. That's what S of t stands for. That's a function of time in seconds. So first question here, or first part, what is the change in vertical position of the bungee jumper between these 2 points? So basically vertical position or height are given by this function. So if we want to find the change in position, we can evaluate this function at both those points and find their difference. So let's go ahead and do that. So basically I want to find S of 0, which will be 100 times cosine of 0.75 times 0 times e to the negative 0.t2 times 0 plus 100. So a lot of these things are going to go to 0. So cosine of 0 is 1, so we get 100 times 1 times e to the 0, which is 1, plus 100, which is equal to 200. And what are our units? They are feet. So 200 feet. And S of 15. So again, we can plug in these values. So 100 times the cosine of 0.75 times 15 times e to the negative 0.2 times 15 plus 100. Give me a second to calculate all this. By the way, if it hasn't already been said, we should assume that anytime we're dealing with a trig function, we're going to be dealing in radians rather than degrees. So 0.75 times 15, take the cosine of that, times 100. So I'm using my phone, so let's do this in pieces. So I get 25.169 times e to the negative 3. What is e to the negative 3? .04979 plus 100. So final result is all right. Final result is 101.25. So from there, we can get this difference. So S of 15 minus S of 0 equals 200 minus 101.25, which is 98.75 feet. So again, we're not asked for a rate of change yet. This is simply about over, this interval. So from t equals 0 to t equals 15, what is the change in y value? So from 200 down to, slightly above 100. So what do we have here? Our delta t was equal to 15 seconds. And what happened to the mark that I made? And our delta s is equal to 98.75 feet. In fact, I did something wrong here. These are in reverse order. So this should be 101.25 minus 200. So our change should be a negative number, which makes sense because we dropped in height. So that is that change. So moving on to part B. Estimate the jumper's average velocity. So I'm going to lean on the word estimate, and I'm going to read these values from the graph. I know we could do this more exactly, and you might have done this more exactly by plugging in these numbers, but let's read these from the graph. So we've got 4 different intervals here. For the first one, we actually did get these exact numbers, so let's go ahead and use them. I want to find the average velocity. So how do I find average velocity from the things I have? So I'll use V bar, V for velocity, and the bar over the top signifies an average quantity. How do I find that? Well, how do I find velocity in general? That's a change in position over a change in time. And these are the things I just wrote down. What was our change in position? That was negative 98.75 feet over a change in time, which is 15 seconds. So what does that come out to be? 98.75 divided by 15 is negative 6.58. So what does it make sense for the units to be here? Well, I'm talking about a change in position measured in feet, divided by a change in time, which is measured in seconds. So it makes sense that our rate should have that unit, negative 6.58 feet per second. Okay, so let's look at a much tighter interval. So from 0 to 2. And really, all these calculations are going to be done the same way. The only real differences are going to be what I use for my values. So what is my change in height? So do S of 2 minus S of 0 over 2 minus 0. What is S of 2? So here's T equals 2. I'm going to say 100. It looks like it's pretty close to exactly 100. So 100 minus 200 over 2. So that comes out to be negative 100 over 2. So negative 50 feet per second. So that's a much more significant speed. Next, 1 to 6. So what's happening from 1 to 6? And like I said, we can just kind of mimic just take the structure of all these. Remember that I said in the previous video, the average rate of change really is a slope calculation across two different points. So I'll do S of 6 minus S of 1 over 6 minus 1. Let's estimate what the position is at 6 seconds. Looks like we're a little bit less than 100. I think we can say 90. By the way, I'm estimating, so my numbers might be slightly off from yours, especially if you really did plug into this formula, but that's okay. And what's happening at 1 second? Let's say 150. So 90 minus 150 over 5. So that's negative 60 over 5. So that should be negative 12 feet per second. And then finally, all right, so lastly, S of 10 minus S of 8 over 10 minus 8. Got 2 more values to estimate. So at P equals 10, I'm going to say about 105 minus S of 8, which is going to be about 120. So 105 minus 120 over 2. That'll be negative 15 over 2, so negative 7.5 feet per second. So is that all 4? I believe that's right. I'm going to double check these because they all came out negative, and I want to make sure that makes sense. So from 0 to 15, yes, we decreased in height, so that should be a negative average velocity. From 0 to 2, also a decrease in height. From 1 to 6, also a decrease in height. And finally, from 8 to 10. Okay, so they all should be negative because in every single one of those intervals, our height at the beginning of the interval was greater than the height at the end of the interval. So over some positive separation in time, we have a decrease in position. All right, moving on to part C. On what time intervals do you think the bungee jumper achieves her greatest average velocity? So, greatest average velocity, like we just said that her average velocity on every single one of these intervals was negative. So I'm going to answer this in a couple different ways. One in the way that it's, technically written, and one in a way which I suspect what they were really looking for. So, where does the greatest average velocity happen? Um, so if we want to think about that as being the least negative, that would be from 0 to 15. And that's because, I mean, that's a very long separation in time. And even though that also has her greatest change in displacement or greatest change in position, you're dividing by a very long separation in time, 15 seconds as opposed to 2 or 5. So that's the least negative. So technically the greatest change she has, or her greatest average velocity. The other interpretation of this question, what's her, greatest average speed, or like the greatest magnitude or greatest absolute value of her average velocity, that is going to come from the interval from 0 to 2. So where she's, moving downward, but her average velocity was 50 feet per second. And, hopefully that makes some intuitive sense, because if you think about when someone bungee jumps, like they're under free fall for, the first part of their journey. So for the first 2 seconds, it looks like, basically it's just gravity. So her speed is increasing. She's losing quite a bit of position over a relatively short period of time. So let's move on to part D. Estimate the jumper's instantaneous velocity at t equals 5. So all we can do here is estimate. Let's see if we can rely on some of our previous answers here. So do we have an interval that includes t equals 5 seconds? Well, we do. We have, the interval from 1 to 6. So let's write this down. On the interval from 1 to 6, her average velocity was negative 12 feet per second. So that is an estimate, but I think we can do a little better, because there's still a pretty wide interval. So if we're going to look for t equals 5 and try to estimate her speed there, let's tighten the interval and let's do 4 to 6 seconds. So that's t equals 4, t equals 6. And let's look at the average velocity over that. So the average velocity is going to be equal to s of 6 minus s of 4 over 6 minus 4. We already said, let's just be consistent. What do we say s of 6 was? 90. 90 minus s of 4. So s of 4 looks like she's very near the bottom of her jump. It looks like 55. So 90 minus 55 over 2. So 45 over 2, let's say 22.5 feet per second. So again, just to kind of look forward a little bit, there are ways to get better estimates here. One, if you plug in t equals 4 and t equals 6 of this function, you can get much more accurate numbers and get a much more accurate average velocity. Also, very, very shortly, we're going to learn how to take derivatives of functions that look like this. And when you do that, you can, like, we don't even need 2 points. We can just find the instantaneous velocity at that 1 point. But for now, I think this is a good estimate. One thing I do want to point out is that this is a positive. I believe this is the first, this is the first positive value we've gotten for an average velocity. So what does it mean that that average velocity is positive? So I'll go ahead and hold that, because I think, yes. So the next question attends to that exact thing. So among the velocities we computed, which are positive, which are negative? What does negative velocity indicate? So we talked about negative velocity when this first came up in part B. Let's just talk about what it means for an average rate of change. Average rate of change is, generally speaking, your change in output values of a function over whatever the corresponding change of input values is. So what are our input and output values for this function? The output values are height, so some vertical position, and the input values are time values. So what do you get when you divide a position by a time span? That's a velocity. In this case, it's an average velocity because I don't care about what's happening in between the two endpoints. I just care about what's happening at the endpoints, finding the average. So everything we looked at on part B, every one of those intervals, this jumper lost height. So that's why these average velocities are all negative, as opposed to what's happening at t equals 5 seconds, you know, from here to here. That's when she's on the rebound. So her height is increasing because she's bouncing back up. So that's the unique case that we saw where her average velocity was a positive value. So in general, yeah, negative velocities are going to refer to your position decreasing, and positive values of average velocity are going to correspond to your position increasing.